Dhruv and Vineet. Okay, now let's understand a question related to this.
Sir, one.
Okay, so this is clear, na? 4T by R excess pressure of the air inside.
So what is P dash exactly?
Okay, now let's do a numerical problem related
So
to
what
this.
is
So,
P dash exactly?
sorry, I couldn't hear your question. Can you come again, please?
So what is P dash exactly?
P dash is the pressure of the, the liquid in the shell, there's a thin layer of liquid now. So that exists at some pressure. So that pressure is P prime.
Okay.
Okay, so there are basically three different pressures: the pressure of the air outside, the pressure of the liquid in the shell, and then the pressure of the air inside the shell. And that's why that formula is being applied twice now.
Okay, sir.
Okay, now the question. So you have two spherical soap bubbles. They are having radii, let's say 3 millimeters and 4 millimeters. In fact, let's make them centimeters. So 3 millimeters and 3 centimeters and 4 centimeters. Okay, floating in air. Come in contact and stick together such that a certain part of their outer surfaces remains in contact. But their shells do not break. So we have to find the radius of curvature of the portion in contact. And show its shape, that is which side the curvature is in a diagram. Okay, just try out this application question. So this is a direct application of the formula that you're seeing above. Okay. Okay, so let's understand what's happening in this particular situation. So if you visualize the two independent spherical bubbles, they're like two thin shells, but of different radii. So therefore having different amount of pressure of the air inside. Okay. So this one is at pressure P1, let's say this one is at pressure P2. So P1 is equal to P0 plus 4T upon R1. P2 is equal to P naught plus 4T upon R2. R1 is 3 centimeter, R2 is 4 centimeter. So you can see that P1 is greater than P2. T is same because T is the surface tension of the soap solution. They are both soap bubbles of the same solution, so same material property. Now, as they come in contact, what will happen is that the shape will distort a little bit where they come in contact, because the pressure difference across that common wall becomes different. Okay, so I'm just drawing a bit of a magnified diagram of them in contact. So this part, the air still more or less exists at pressure P1. This also exists at pressure P2, but that pressure difference is less than P0 minus P1 or P2 minus P0, like that. So there will be a difference in curvature of the common part of the wall. It will be like this. So the common part of the wall, now it will be concave on the side which has higher pressure. It will be concave from this side. So its radius of curvature is, let's say, small r, whereas this one is having a radius of curvature R2. This one is having a radius of curvature R1. Its center of curvature will be at a different point. Okay? So across this wall, you can see that P1 is equal to P2 plus 4T by small r. This is my equation 1, this is my equation 2, this is my equation 3. So from this, you can see that P1 minus P2 is equal to 4T by r. And from this, you can see P1 minus P2 is equal to 4T 1 by R1 minus 1 by R2.
Sir, can you explain equation 3 once more? I didn't understand that.
The pressure difference across a spherical surface is 4T by R. No? So the concave side always has higher pressure. So this is some new concave side of radius. I mean, this is the common wall, but its concavity is different. Its radius of curvature is small r now, and this side is concave. The concave side has higher pressure than the convex side by a factor of how much? 4T divided by R. Is it clear now, Vita?
Yes, sir.
So now comparing this equation and this equation, you can see that 1 by R is equal to 1 by R1 minus 1 by R2. When you substitute, this will give R as 12 centimeters. And it will be concave on the side which is having the smaller radius of curvature. Okay. As the two bubbles are in contact, the smaller bubble side will have the concavity in the common part of the wall, and the bigger bubble side will have the convex. So this is the convex side. This is the concave side. And you can see it's a much gentler curvature compared to this one or this one, because these are having radii 3 and 4, and this is having radius 12. Okay, so hope this question was clear. Now we move on to another phenomena related to surface tension, and that is the concept of capillary action and contact angle. So basically what happens is that you will notice that when you keep a liquid in a container, or basically any liquid is in contact with some kind of a wall of a solid material. So the surface of the liquid is actually in contact with another material at the corner. Okay. Typically, there is always a curvature over here, and most often the curvature is this way. Sometimes the curvature can be the opposite way also, such that from the outside this looks like a convex surface, but mostly from the outside it will look like a concave surface at the corner like this. So this, if we now observe this situation under a magnified diagram, so what we will see is, like suppose this is the outer wall of our glass container. And suppose this is something typically like water. Okay. So the surface of water where it comes in contact, it's bent like this. And where it is in contact with the glass wall exactly, if we draw a tangent to the surface, and that tangent makes an angle theta with the, or theta c with the vertical, and that is called the angle of contact. So the contact angle is the angle of the surface that is a tangent to the surface at its point of contact. With respect to a vertical solid wall or surface. Okay. That is called the contact angle. And typically here in an example like this, the contact angle is going to be an acute angle, like in the case of water and glass, because what happens is that now the molecules at the surface near this wall where the contact angle phenomena is there, if you look at molecules here, they experience a combination of two types of forces. They experience very strong or comparatively stronger adhesive forces and comparatively weaker cohesive forces. So adhesive forces, which are the forces between the unlike molecules, that is between glass molecules or whatever that solid is and the liquid molecules, they dominate over the cohesive forces. Cohesive forces are attraction between like molecules, so water molecules. Okay. So because they dominate, so that pulls the surface up at the point of contact a little bit like that, and that creates this phenomena of a contact angle which is acute. So for glass and water, the contact angle is acute. In fact, it's very small. It's almost tending to zero for glass and water, because adhesive forces, that is intermolecular attraction between glass and water, dominates. Over cohesive forces. Cohesive forces, we already understood what they are before, that they are the intermolecular attraction force between like molecules, so between water molecules. But so typically, this is the situation that happens for most pairs of of a liquid in contact with a solid. The contact angle is acute. Because this is what happens, because adhesive forces dominate. But there is one very common notable exception, and that is the case of mercury and glass. The case of mercury and glass, the cohesive forces dominate, and that's why mercury bends the other way at the point of contact. So there is a obtuse angle of contact nearly equal to 135 degrees. So this is again an experimentally observed phenomenon. So for any given pair of materials, that is one liquid and one solid, there will be a certain value of contact angle, which is their material property. It is a material property for that pair of materials. So water and glass will have a different contact angle with, in comparison to, for example, wood and glass, or plastic and glass, or some metal and glass, or some other liquid with respect to glass, etc. Okay, Ansh, I'm taking you back to the previous section for a minute. You can, if you missed out noting something or you have any doubt, you can discuss with me. Just a moment. Yeah, Hitansh, if you have any doubt in the equation solving, please let me know in this previous question. Okay, so these two equations are showing you the pressure of air inside each of the bubbles. So when they come in contact, their common part of the wall which is in contact, it is an interface between air on one side which is at pressure P1 and on the other side which is at pressure P2. So P1 minus P2, that pressure difference has to be such that it is accommodated by that particular radius of curvature, because for a spherical surface of radius r, the pressure difference across it is 40 by r. That's how we are getting that formula. So 1 by 3 minus 1 by 4 will finally give you 1 by 12. So that's how small r is coming out to be 12 centimeters. Hope this is clear. Yeah, Hitansh, you understood now. Very good. Okay. Yeah, so coming back to concept of contact angle. So exception cases are there where the angle of contact can be obtuse, like in the case of mercury and glass. because the adhesive forces are weaker compared to the cohesive forces. Certain exceptions like mercury and glass interface have an obtuse value of contact angle, because in such cases the cohesive forces are dominant. Okay, so that kind of interface would look like this now. So if we have a glass container which has mercury in it, so what we would typically observe is that the mercury is bent like this at the side. In the mercury surface, slightly bent like this. So if we draw a tangent to the surface at the point of contact, that tangent with respect to the vertically upward direction, it will be making an obtuse contact angle. So the value of this contact angle is a property for the pair of materials, the solid and the liquid. And is experimentally measured. So that is our concept of contact angle. Now we'll see how this contact angle plays a role in the capillary action concept, that if you dip a narrow capillary or a thin cylindrical pipe into a liquid surface, the level of liquid within the capillary rises. So that happens partly because of this phenomena of contact angle and the property of surface texture. Okay, so let's observe how that happens. Capillary action or capillary rise.
Sir, can you scroll back one?
Yeah. This partner.
Yes, sir, done.
Okay. So now we come to the final part of surface tension, capillary action or capillary rise. So I think single P and double L, if I'm not mistaken. So what we observe is that if you have an open surface of liquid, this might be in a vessel, this might be like a body of liquid, like a lake or pond or whatever. And in that you dip a thin tube. And typically we're talking about a cylindrical, a capillary by definition is actually a thin cylindrical tube. though this whole thing of liquid rising will be observed even in a non-cylindrical shape. If you have, something with a square cross section or even an elliptical kind of cross section, you will observe capillary action. But I mean, you will observe liquid rising. So let's say this is a glass capillary, and this is again some kind of soap solution or something, can even be water for that matter. So what we will observe is that liquid rises, and also that the liquid surface inside the capillary is different in shape. It is what is called a meniscus. It's a spherical surface. It's a section of a sphere. So this height by which the liquid rises, that's called the capillary height. And among other things, so a capillary is definition a thin, open, cylindrical tube. So this glass capillary has a radius of capital R. So now let's understand why this exactly happens, why the liquid rises. So sort of making a, again, a magnified diagram of the capillary. So what happens is when we dip this capillary into the liquid, because there's air inside it initially, so the liquid will push out that air, okay, and take this. But because of the the phenomena of cohesive and adhesive forces, the liquid surface that is inside is bent like this at the contact angle, which is at material property. So if I draw, so that's actually what causes the liquid to rise, and I'll explain why it causes liquid to rise. So what happens is that the liquid inside the surface forms a meniscus. That is, it is a spherical surface, concave from outside, of liquid inside the capillary. It's like a concave bowl kind of thing also. So that is happening because of that relationship between adhesive and cohesive forces. The cohesive forces are dominated over by the adhesive forces that the glass is applying on the liquid molecules at the surface of contact. So that's what makes them rise. Okay, and that creates this kind of contact angle over here. So you have to imagine this in 3D. It's like, so that surface of liquid itself is like this. It's like a bowl like this. So it's making a contact angle like this. This angle is the contact angle. So now if we draw a normal at the point of contact, that is the radial direction. So where the two normals will meet, that is the center of curvature of the meniscus. This C is the center of curvature of this liquid meniscus. So let's say the radius of the meniscus is small r. So this is the contact angle, which is basically a property of the liquid and the solid combination that we are using. And C is the center of curvature of the meniscus or the concave liquid surface. So small r is the radius of curvature. Of the meniscus. So first of all, we can see there's a relationship between the radius of the capillary, which is this one, and the radius of that meniscus. So if we just draw this here, okay, so you can see that this angle will again be contact angle, and this is r. So from the geometry of that triangle, we can see that small r is equal to capital R by cos theta. So now what happens is that this meniscus created, it creates a pressure difference. So the other thing to understand here that there will be a pressure difference of delta P equal to 2T by small r across this concave meniscus. And always the concave side has higher pressure. So going back to this, so the pressure just a second people. Okay, so now this concave surface, it has a pressure across, the pressure difference across it such that the pressure difference is created by that curved nature of the surface, because it's stretched out, there are elastic forces. So always the point inside the concave part is at higher pressure. Okay, so that pressure difference is created such that PA minus PB will be equal to this pressure difference of 2T by R. But A is a point on the open atmosphere, so that creates a lower pressure at the point B just inside the meniscus. It becomes atmospheric pressure minus 2T by small r. Okay. So that is why when liquid comes inside, now that meniscus cannot remain at the same level as this, as a liquid on this, because then the pressure at this point and this point will be different and more liquid will come in. Okay. So that's why the liquid rises inside, so that this pressure difference is compensated for by this vertical pressure difference. So now if you see between the point B and C, if there's a vertical height of h and this point is D. So now you can see that the pressure at the point C will be pressure at the point B plus rho gh, and that should be equal to pressure at the point B, which should be equal to atmospheric pressure. So PC, which is now equal to pressure at the point B, which we can substitute from here. So P naught minus 2T by R. This pressure difference of 2T by R now gets compensated by the amount of liquid which has risen. So that again at this point C, the pressure is the same as the atmospheric pressure. So you can see from this that 2T by small r is equal to rho gh, or h is equal to 2T divided by rho into small r into g. And small r is the radius of the meniscus. So we'll express it further in terms of the radius of the capillary. So that will become this. So this is the derivation of the other formula which is important, which is the capillary rise. Okay. It is inversely proportional to the radius of the capillary and the density of the liquid. So here T is surface tension. The same fluid. So this is the other important formula. So two important formulae while doing problems. One is the relationship between the radius of the meniscus and the radius of the capillary. Okay, and of course, we've seen earlier already that theta c is the contact angle. Okay. So this is the phenomena of capillary action. So I'll just take you through this section fully once. So this kind of situation where you dip a capillary into an open liquid surface, you see that the liquid rises within the capillary and the surface of liquid inside is in the shape of a concave bowl kind of thing. So that's called a meniscus. So the radius of curvature of that meniscus and the height of the capillary, I mean the height of the liquid inside the capillary, both can be calculated by this derivation. So just make a note of the key points over here. Then we'll discuss a numerical application or two based on this. And then we are done with surface tension. So we'll start with viscosity, which is the last part of this chapter. Okay, so I'm just scrolling down to the final part of the derivation. Okay, so now as far as questions are concerned, most of the questions in this part are straightforward formula based, but there are one or two types of variations possible. So we'll quickly discuss an example. Let's say we have this situation that capillary inserted in a liquid is observed to result in capillary rise of 4 centimeters, okay, and a contact angle of 37 degrees. Okay. Now the capillary is slowly pushed further into the liquid until only 3 centimeters of it is above the surface. Determine the shape of the meniscus. Okay. And any change in the contact angle. Okay. Will liquid be continuously pouring out, or will it reach an equilibrium? So let me explain the question. So what is happening is that we have some liquid surface. Now we have done in the normal situation, we've got a thin capillary which is sufficiently long. The part outside is sufficiently long. And when that is the situation for us over here, what we are observing is that liquid rises inside it up to a height of 4 centimeters. And the contact angle that it makes, meniscus, this is 37 degrees. Okay. But now what we do is we push the capillary further in so that only 3 centimeters of the capillary is left outside. So we do this. Same capillary, same liquid, everything same. Only this much of the capillary is outside. So what is the liquid going to do basically? You have to understand that. That's what we have to answer. Will the liquid be continuously be pouring out? Will the shape of the meniscus change? Will the curvature of the meniscus change, or will it remain same? Will the contact angle change, etc.? All these things we have to see. Will liquid be continuously pouring out? So these are the things that we have to figure out in this situation. What happens here? This is a situation that is given to us. Just try out this question. Snigita, you're partially correct that contact angle will change, but not in terms of the value you have set. Okay. So actually, people, if you just review the whole concept of capillary action, why it happens, because the liquid rising inside the capillary, it forms that concave bowl kind of surface that creates a pressure difference. That pressure difference sort of, it creates a suction, so the liquid comes up. So the liquid comes up to compensate for that pressure difference that is created because of that shape of the surface, that natural shape because of the natural contact angle. So think in terms of that and you understand sooner or later what's happening. Yeah, students, I had got disconnected. Yeah, Kevin, your answer is correct. So basically, that's correct. What will happen is that, if you visualize how the fluid is initially rising because of that pressure difference created, and as it rises, the pressure at this point becomes equal to the pressure at this point. So it stops coming into the capillary further. Okay. But here, as the liquid height reaches 3 centimeters, for that contact angle of 37, which is the natural contact angle, the pressure difference is still not balanced. So more liquid comes in. Okay, and that changes the shape of the meniscus because the liquid can't go further up. So the shape of the meniscus will change in such a way that it becomes flatter, or the radius of curvature of the meniscus will become less, which means the contact angle will increase. If it was perfectly flat, the contact angle would have been 90 degrees. Okay, so it won't be perfectly flat because there is some capillary rise, but it's not up to the value that is required for the contact angle of 37 to get compensated, the pressure difference because of that. So instead, the excess pushing of liquid from below as liquid rises, that causes the curvature of the surface to change. Now the meniscus becomes flatter in comparison to the first diagram, where it was a natural contact angle for that pair of materials. So this contact angle is some new value, theta, let's say. So theta prime, let's say. So it's the same derivation that we've done for the original capillary rise formula. If you just replace it with a new value here, see that same thing will apply. So this new radius of curvature, let's say r prime, it becomes such that the pressure at this point, and therefore the pressure at this point, so 2t cos theta prime upon capital R, where capital R is equal to rho g h prime. Whereas in the earlier diagram, we had, when there was unlimited amount of capillary available, we had the formula that this h was 4 centimeters for critical angle equal to 37 degrees. So now compare these two equations, this equation and this equation. So you see that the contact angle now changes to 53 degrees. And the shape of the meniscus changes in such a way that it becomes less curved. The radius of curvature has become larger, so it's not so sharp, it's flatter in comparison. So if you bring the tube all the way down to the level of liquid, the open surface level, the meniscus should completely flatten. Okay. Now the thing is, of course, we are doing this in such a way that the capillary was in this kind of situation first, the first diagram, and then you're pushing the capillary in. So when you initially push the capillary in, as the amount of capillary outside starts reducing from 4, liquid will come out. Okay, so some liquid will gush out, but it's not that once you have brought it to that 3 centimeter position, the liquid will eventually achieve this kind of equilibrium at the new value of contact angle. It is not going to continuously keep gushing out like a fountain. So that is what the meaning was for that other part of the question. Okay, so hope this example is fully clear. Okay, so this is a variation of the normal kind of situation of contact angle and capillary rise formula. So very simple chapter of surface tension. If you just remember the 3 or 4 different formulae and the properties of the phenomena related with surface tension, you should not have any difficulty doing the questions. If you do HC Verma plus your module, it's more than enough. Okay, don't waste too much time on this chapter. Just do what is required to score the full marks at JEE level. In any case, it doesn't have too much weightage. Typically, maybe just one question from surface tension. It's not one of the very important chapters in that sense, but at the same time, the question will always be easy from surface tension, so you should not ignore it so that you make sure you score the marks. Okay, now let's move on to the next and the last part of properties of matter, which is viscosity. So viscosity is the property of a fluid, non-ideal fluid, by which it tends to oppose slipping and relative motion and dissipate mechanical energy. Okay, so it's in that sense it is an equivalent of kinetic friction, but in many ways it's different from kinetic friction, which is also what we'll understand. So viscosity is the property of a non-ideal real fluid by virtue of which there is dissipation of kinetic energy during flow and it opposes relative motion. So what we mean by it opposes is that viscous force, or it can even be called drag force. So it's a dissipative, non-conservative kind of force, which brings it in the category of kinetic friction. Okay. However, one major difference is that the amount of viscous force actually depends on the relative motion, which is not the case with kinetic friction. Whether an object is slipping on a surface with a relative velocity of 3 or 5 or 100 meters per second, it doesn't matter. The kinetic friction only, the amount of kinetic friction acting depends only on two things: the nature of the two surfaces in contact, the materials of the surfaces, and the pressing force between them, or the normal contact force. Here, that is not the case. That's where viscous force becomes different. Okay. So one thing is viscosity is applicable for all fluids, including gases. Okay. So viscosity is observed in fluids, that is liquids and gases. So air drag, which is something that you ignored in projectile motion earlier, but you cannot ignore if you have a lightweight material like a piece of feather or something which is floating down in air. You cannot neglect the air drag compared to the weight. So such an object will not be in free fall under gravity. It will also be influenced by a significant amount of viscous force or air drag force. So now viscosity is studied in two contexts. One is viscous forces acting between the layers of a fluid which are in relative motion. With respect to each other. Okay. And the second is when a solid body moves through a viscous fluid. Okay. Actually, even another liquid can be moving through a given liquid, like raindrops falling through air also experience viscous or drag force, and raindrops are not solid objects, they are liquid droplets, but they are moving through another fluid of air. So it can be a solid body, or it can even be or one fluid moving through another. The example of that being rain falling through atmospheric air. Whereas an example of the above one is, let's say, any stone falling through a liquid. So you'll actually experience, in addition to gravity, two other forces, buoyant force as well as viscous force. So these are the two situations in which we observe viscosity. So we'll start with the first situation. Okay. Viscous force or viscous forces in a fluid in something called laminar flow. Okay. So laminar flow is that situation where, due to the viscosity, the liquid is flowing in such a way that different layers are moving with respect to each other. So is flow of a viscous fluid such that layers of fluid move relative to each other. Such that there is what we call a velocity gradient across a cross section of the flow perpendicular to the direction of flow. So one easy way to visualize a laminar flow is a laminar flow with a uniform velocity gradient. So imagine we have something like this. This we are observing from the side, a stream or something like that in flow. So this is muddy water of canal or a stream. So now if we visualize a very sort of idealized situation where the velocity vectors have a uniform vertical gradient. That is, if we observe the velocity vector of these liquid molecules at any position, we will see that as we go down the water canal, like if we go deeper and deeper, the velocity is decreasing uniformly or linearly. It's like there are different sheets or laminars of liquid which are flowing relative to each other across the cross section. So if the velocity is v at some general position, for a layer just above it, it is v plus delta v. For a layer just below it is v minus delta. So if we call this as our y-axis, we can see that there is a uniform gradient for the velocity, delta v by delta y. So this is an example of a laminar flow. There's a uniform velocity gradient. So that gradient is now, suppose at the top the velocity is v naught and the total depth of this is d. So you can see that there is a uniform velocity gradient equal to v naught by d. So that is the slope of this. So if you were to think of plotting a graph of the velocity with respect to the depth that you're considering, actually that gradient is a negative quantity because with the depth it's decreasing. So you will see that your graph of velocity versus depth is like this. Where the slope is minus v naught. So this is an example of what we call a laminar flow, and in this case it's a laminar flow with a uniform gradient, uniform velocity gradient. Anything where physical quantity is changing with respect to position, we say there's a gradient. Like you've seen in work by energy, potential energy gradient or negative of potential gradient is internal conservative force. Okay, electrostatics also you've seen that electric field is negative gradient of potential, electric potential. Okay. So something changing with position, we say there's a gradient. Something changing with time, we say there's a rate of change. So this is that gradient. So velocity is changing with position. So there's a velocity gradient across the cross section such that the direction of that gradient is perpendicular to the direction of flow. So velocity is varying with the y-axis. So it has a gradient with respect to y-axis, whereas the flow is happening along the x-axis. So that is a situation of laminar flow. And that laminar flow is actually created because of viscosity. If the liquid had been an ideal fluid with no viscosity, it would be in steady flow. So there would be a uniform velocity through the cross section. There wouldn't be a gradient. So this whole phenomena of laminar flow is exclusively observed because of the viscosity of the liquid. It doesn't happen in the case of an ideal fluid, which is in steady flow. Now that's the thing, Nikita, the velocity need not be zero at the bottom, but here in the diagram, I'm assuming that just at the bottom, at the bed of the canal, the velocity is tending to zero. It need not be the case. It actually depends on what external pressure gradient is being applied across the x-axis, which is causing the liquid to flow at what kind of rate, etc. So here's a very simplified example with a uniform gradient such that the velocity is zero right at the bottom and is v naught at the top, and it varies uniformly with depth between the top and the bottom. So that is for this particular example. It need not always be the case. Yeah, so Aditya, if you are imagining a situation like this where you have a canal and the the liquid is in it is like highly viscous because there's mud mixed with water. So what is happening? The bed of the river that's trying to stop the liquid from moving. So maximum like dissipation of energy is happening right at the river bed. So that layer is moving slowest, and as you go above and above, there is more and more freedom for the liquid to move. So that's what's creating the velocity gradient naturally. Whereas had the liquid not been viscous, this would not have happened. The liquid would just be flowing uniformly. Or you can imagine a situation where we are creating some disturbance at the surface, which is causing the layer at the surface to move. But the next layer below it is not moving that freely because there's viscosity between those two layers. Then the next one even less freely, like that. So it's basically viscosity which is hindering the motion. It's creating a opposition to relative motion. Just like in mechanics, you had a situation of multiple blocks kept on top of each other. Now, if you were to apply some impulse or continuous force on the topmost block, that one would be moving fastest. But as you go down, the speed of the blocks would start reducing because more and more friction. Okay, so that kind of situation. So now, what we experimentally observe about viscous force is that if you consider a surface of liquid in a laminar flow, the surface of an imaginary surface of liquid, or you can say the surface of a volume element of liquid, it experiences an amount of viscous force, which depends on various factors. Among that, the surface area. Okay. So in that laminar flow that we were seeing above, just imagine a volume element of liquid flowing like this. So this thin layer of liquid is moving at a speed v. Okay. So it's somewhere here basically in the cross-sectional diagram. Right above it, there's another layer of liquid which is moving a bit faster, moving at v plus dv, let's say. And right below it, there's another layer of liquid that is moving a little bit slower. So that's how the velocity. So if this surface of that sheet of liquid has area A, then because the layer above it is going faster, so it will experience a viscous force in this direction. Just like if you make a block on top move faster, it will apply a friction. The tendency for slipping is in the backward direction for this one with respect to the one above. So this one will experience frictional force, or in this case viscous force in this direction. So viscous force on a surface, okay, of area A, okay, of the fluid, the magnitude of that viscous force is directly proportional to the surface area and to the magnitude of the velocity gradient. This is our y-axis in this case. So here, this is velocity gradient perpendicular to the direction of flow. Okay, that is the direction of V itself. And now the constant of proportionality is basically the material property of that particular fluid, which is called the coefficient of viscosity. Denoted by the same symbol eta, as you have seen for modulus of rigidity and elasticity, but it has no connection with that. It's a totally different quantity. So this is called the coefficient of viscosity. And unlike coefficient of friction, it is not a dimensionless term. It has a unit. You might have heard the term poise. Yes. So the dimension of coefficient of viscosity is the dimension of force, okay, into the dimension of time. As you can see, dv by dy has force per unit area. Because dv by dy has the dimension of time inverse. Okay, so So 1 poise is equal to 1 Newton second per meter square. Another way to define 1 poise would be that you can say it is 1 Pascal second. Newton per meter square is Pascal. So for example, water has a viscosity of approximately about 0.9 millipascal or millipoise. Then, for example, something like ethanol has a viscosity of about 1.1 millipoise. You don't have to remember the values, I'm just giving you an idea. Mercury has a viscosity something like around 1.5 at room temperature. Glycerol is something which has a very high amount of viscosity. At room temperature, it has like almost 1 poise, 0.9 poise, 900 and something millipoise. This is all I'm saying, more or less at 25 degrees C room temperature. Whereas, for example, if you take something like aluminium or gold or something at very high temperature where it's molten in liquid form, and again it has a comparatively high viscosity. So there's a lot of research in material science done about viscosity and a lot of experiments, etc. And there is no direct correlation between things like density and molecular structure or molecular weight or anything like that, because viscosity depends on a whole lot of factors, not just simple factors like density. It depends on the nature of intermolecular bonds, whether it's polar molecules or whether there are van der Waals forces or hydrogen bonding, etc. All these factors will affect the viscosity. Oh, I have written coefficient of friction, is it? Sorry.
Yes,
It's
sir.
coefficient of viscosity. Yeah. Very different from coefficient of friction. Thanks for pointing out. So that's about the coefficient of viscosity. So let's see a typical numerical problem to understand this. So now imagine you have like a very thin layer of highly viscous liquid, like glycerol or something like that. Or you have maybe some oil, castor oil or something like that, forming a very thin layer on the ground below. So this is the ground. And this thickness is, let's say, 2 millimeters. And this is a fluid which has coefficient of viscosity pretty high. So let's say it's about 0.9, capital P. Now we have something like, let's say we have a small piece of cardboard or something which is floating on top. Or plywood or whatever. So this is, let's say, a cardboard sheet. And what we want to do is we want to push it with some external force so that it maintains a uniform velocity. So in the 3D picture, you can see that the cardboard sheet will be something like this. So this cardboard sheet has surface area given to us. The surface area is, let's say, 50 centimeters square. Okay, and it's floating on this layer of castor oil or glycerol or whatever, which has this kind of viscosity and this thickness. So we have to find the force needed to keep this moving at a constant speed of v1. Of, let's say, 6 meters per second. Okay, so it's just like if you have a rough surface which has a coefficient of friction, to keep a block moving at constant speed on that horizontal surface, you'll have to apply a force that continuously balances the kinetic friction. The moment you withdraw the force or reduce the force, it will start decelerating. The same happens in the case of viscosity. Okay. So what will happen is that cardboard layer, as you're pushing it, it will start dragging the top surface of the oil along with it, or the fluid along with it, creating a laminar flow of liquid. And once that liquid is in laminar flow, it's your viscous forces or drag forces are going to come into play. So you will have to continuously apply that external force to overcome those drag forces. Okay, so I'll just verify the calculations that you are sending me. So basically, we'll have to assume the simplest possible situation here, that we have that laminar flow with a uniform gradient. Okay. And the layer of oil which is in contact with the ground below, that is almost at rest. So you'll have to understand that the laminar flow of the liquid will happen in such a way that the layer on top is almost moving with the cardboard sheet, so it's moving at V0, and the layer in contact with the ground is almost just about at rest. So we have this kind of a velocity gradient. So taking this as our y-axis, our delta V by delta y, or dv by dy, whatever, that is minus V0 by this height h. It is equal to minus of 6 meters per second divided by 2 into 10 raised per minus 3 meters. So it is so now on that cardboard sheet, from below there is a viscous force acting in this direction. And that has to be overcome with the external force, so that it keeps moving at a constant velocity and its acceleration is zero. So the external force has to balance the viscous force, which will be coefficient of viscosity into area into magnitude of this velocity gradient. So the surface area we had taken to be 50 centimeters square. So in meters square is this much. Okay. And this is 3 into 10 raised by 3. So this is meter square. This is uh, per second. Okay. And this is poise or Newton second per meter square. So this force comes out to be in newtons. Okay. So this is an example of the application of the concept of viscosity. So this concludes like the first aspect of viscosity, that is viscosity in a laminar flow. We'll see one more situation of this kind of laminar flow through a cylindrical pipe. That's a somewhat complicated application. We'll see that next time. And the other thing we will see is that the viscosity acting on a solid object, which is moving inside a viscous fluid, including Stokes' law, which is a particular formula for viscous force on a spherical body. You might be familiar with Stokes' law from your understanding of things like Millikan oil drop experiment, etc. in chemistry. So we'll look at that in the next lecture. Just take about probably 40 minutes or so. We'll finish viscosity, and then we'll keep some time for further discussion of doubts and questions in properties of matter before moving on to the next section of physics after properties of matter, which will be oscillations and waves, starting with simple harmonic motion. So we're coming to a very important part of the syllabus now. So unlike properties of matter and fluid mechanics, the next section is going to be a little bit more intense, okay, and also it has more weightage, which is the section of waves and oscillations. Okay. So that's it for today's session, people. Wish you all the best. Thanks for attending. Have a nice day.
Thank you, sir.
Yeah, okay, people.